Welcome to video on linear integrated circuits. We are discussing electrical fat hammer applications, and this is the first video on simulations of monoshot using LT spice. So we should see how do we simulate LT monoshot multivibrator using LT spice. This is a circuit diagram of triple five timer as a monostable multivibrator. The connections are made as per the realization of monoshot. As you can see, there's a resistor R2 and C1 besides the R and C of the monoshot, which will decide the pulse width of the quasi-stable state. And C2 is the capacitor which is used to maintain the voltage at control voltage, which is VTH, which will be 2/3 of VCC. Reset is connected to VCC to make sure that the output doesn't reset. The VCC is connected to this 5-volt supply, and trigger is connected to the pulse where we are giving a trigger signal to the output, and we have shorted the discharge and threshold and connected to this junction of R and C. Now, as per the calculation of pulse width, the pulse width happens to be 1.1 into R into C, which comes out to be 1.1 millisecond. Here you can see we have applied a pulse of initial magnitude 5 and trigger a voltage of 0. So initially it is 5 and then goes to 0 for a point. It remains there in 0 for 0.1 millisecond, and it repeats for every 3 millisecond. So this is what is the pulse description. Initially it is 5, goes to 0. This is your rise time, okay, delay time, rise time, fall time, and this is the time to which it is 0, which is only 0.1 millisecond. 3 millisecond is the repetition time, and we have 10 cycles. Let us run this simulation and try to see what is this is the trigger signal. You can see it is initially high and it is going low for 0.1 millisecond, and it again goes high. This repetition happens for every 3 millisecond. That's what is specified here, and we know that since the trigger signal is going below VTL here it is 1/3 of VCC. Now VCC is 5 volt, so 1/3 of 5 will be 1.66 volts. Since the trigger signal is going below 1.66, now this is a valid trigger signal, and it remains 0 for only 0.1 millisecond. Actually expected the pulse width is 1.1 millisecond. Let us see how does the output looks like. This is the output. Now you can see the output is high for a period of 1.1 millisecond, which is the desired pulse width. And we can also see what is the capacitor voltage, how it is charging and discharging. Now this is the capacitor charging and discharging. We can also see what is the voltage at this CV, which is a control voltage, which will be always constant at 2/3 of VCC. You can see these are 4 different waveforms at different points. So we shall separate out all the 4 waveforms and try to understand how does the monoshot is working. So let us have 4 different planes and try to put them in different planes and try to understand how the circuit works. So let us first put the trigger signal on the top. Next we shall put the output, and we shall also put the capacitor voltage. Now you can clearly see, as long as the trigger signal is VCC, there is no triggering for the output. Output remains in the stable state of 0 volt. So capacitor is now discharging. Now capacitor is fully discharged to 0. Now the voltage at the control voltage is at 2/3 VCC, which is 3.3 volts. Now as soon as the trigger signal goes below 1/3 of VCC or VTL, the output goes high. As soon as this output goes high, the transistor through which the capacitor is connected is now off. The capacitor starts charging towards VCC. As soon as it reaches 2/3 of VCC, which is exactly VTH, the output switches back from quasi-stable state to stable state. Now it's again remaining in stable state. This again goes to quasi-stable state again once you apply the next trigger signal. Now this is the pulse width what we desired for. We expected a pulse width of 1.1 millisecond. Let us try to see what is the pulse width. Now this is the one edge of the pulse. So let me move this to the other edge. Now I can see this is the difference. Horizontal difference is actually the time difference. The difference between the two cursors is 1.09, which is close to 1.1 millisecond. You can also see, suppose if I just put this onto this, now this is actually 2/3 VCC voltage, the control voltage. Now as soon as the capacitor reaches this voltage, output goes down from quasi-stable to stable state. Now this way we can see that once the capacitor voltage reaches VTH, the output goes to quasi-stable state. Let us try to apply different trigger signals and try to verify how does the output changes. Now we shall change the trigger signal and try to see how does the output changes here. So let me go back to the trigger signal and modify it. So let me make this a signal. So instead of making it going to 0, let me make it to 2 volts. It means that the trigger signal is not going below VTL. So in such case, let us see what happens. Let me run the code now. Now this is, now we have a voltage. Now this is the current. Let me just remove this and make it voltage. Let me just see what is the voltage here at this point. Here is the voltage. Let me take out the current part here. So let me take out this current. Now it looks as though the trigger signal is going down, but the output is at this is capacitor voltage 0 and the output is also at 0 volt. So you can see now the output voltage is almost 29.99 microvolt, so which is 0 volt here, meaning since the trigger signal is not going below VTL, the output will not go from stable state to quasi-stable state. Output remains there in stable state because this is not a valid trigger signal. So valid trigger signal is one which has amplitude less than VTL. So this way we have to apply amplitude at the trigger signal to go below VTL so that output goes to quasi-stable state. So we shall again change this to a different combination, try to see how does the circuit works. Now let us change this period. So we know that it will repeat for every 3 milliseconds. Let us ask it to repeat for every 1 millisecond and try to see how does this happens. Let me make it for every 0.5 millisecond. Let us see how does the output looks like. Now let us save this and run it now. Now since the amplitude is not going below VTL, so again the output is not changing. Let me make the output to go below VTL. Let it go to 0 volt and try to see how does the output changes. Let me make it run more than 10 cycles. Let me make it 50 cycles and run the program. Save it and run. Now you can surprisingly see. So let us consider this as a valid trigger signal. So when there is a trigger signal coming over here, now the pulse width, this has gone to quasi-stable state. When it is remaining in the quasi-stable state, you have one more trigger signal. So you have one more trigger signal here. So since it is coming before this pulse width ended, so we're going to still have it as 1.1 millisecond, which is the desired time here. So these two trigger signals will not be considered for considered as valid trigger signal because these two trigger signals are coming during that charging of the capacitor within VTH. So that's why, so these two trigger signals will not be considered as a valid trigger signal because this is considered as a trigger signal which will make the output to go to quasi-stable state, remain for 1.1 second. Just verify here, when the output goes to 0, when it goes to stable state, if the trigger signal is high, so output goes to its stable state. Suppose if the trigger signal is less than VTL, so this will get extended. So we have 1.1 millisecond as a difference. So it remains in the quasi-stable state for the desired time of R into C. So let us apply one more different type of trigger signal and try to verify how does the trigger signal matters in deciding the on time and off time. So let us apply a trigger signal whose width is more than the desired pulse width. Now let me modify the trigger signal in such a way that it is 5 volt for 2 millisecond and it is 0 volt for 2 millisecond. Try to see how does the output looks. Okay, let us modify the timings here. Now here it is 0 for 0.1 millisecond. Let us make it as 2 millisecond. So it is 0 for 2 millisecond and it is total period is 4 millisecond, meaning that the signal is 5 volt for 2 millisecond and 0 volt for 2 millisecond, whereas the pulse width desired is 1.1 millisecond. Suppose if we simulate now, let us see how does the output looks like. The output expected is of 1.1 millisecond pulse width. So we shall see what is the output now. So we shall see how the output looks like. So there is a mistake here. So we have modified this to this would have been 4 millisecond. Now that is fine. Now let me simulate now. Save it and simulate. Now this is what is this is a trigger signal. It is high for 2 millisecond. It is low for 2 millisecond. It repeats. As you can see now, even though the pulse width desired is 1.1 millisecond, if you actually see the this is the output now. You can see as when the trigger signal goes below 0, as long as it is remaining at 0, this output stays there in the quasi-stable state. Now you can see capacitors keep on charging. So you can observe one thing, the pulse width is not exactly 1.1 millisecond, it is more than 1.1 millisecond, meaning to say the pulse width is not decided by the RNC, but it is decided by the trigger signal. You can see now it is 1.99 millisecond, or it's almost 2 millisecond. Since it is extending up to 2 millisecond, this low level, that is the trigger signal is less than the VTL for 2 milliseconds, the output stays there at quasi-stable state for an extended period beyond 1.1 millisecond. You can see here the capacitor is charging beyond VTH. So if you go back and see what is the voltage at which this is charging, so now we can see that capacitor voltage is almost 4.3 volts, which is more than 1 volt from VTH. If you actually go back to circuit and try to find out what is this CV, CV actually corresponds to the control voltage, which is let me just put the CV as well as the capacitor voltage here. You can see the capacitor voltage is going beyond VTH, which is not a correct output voltage. It is so because the trigger signal is extended beyond 1.1 millisecond. This practical pulse width is not matching with the expression for the pulse width, which is 1.1 millisecond. It is purely because this trigger signal is an extended period of 2 milliseconds. So let us try to modify that trigger signal and try to get 1.1 millisecond. You can have a look at this modified circuit diagram before the trigger signal. This capacitor and resistor will ensure that there is a trigger signal which is having a spike-like structure. The output voltage will not be having an extended pulse width beyond 1.1 millisecond. Let us go back and try to see what is the output waveform. I can clearly see, since even though the magnitude of the trigger signal is less than VTL for more than 1.1 millisecond, but the output stays only up to 1.1 millisecond. So this is the advantage of having that differentiator. So even though this is of a very long duration, the pulse width of the output voltage is still exactly 1.1 millisecond. This is happened because of that differentiator circuit. You can also have a look at how does that differentiated waveform looks like. You can see the waveform over here. So this is how the waveform looks like. So it is giving a differentiated waveform so that you have a spike of voltage going below VTL